So in this video we're going to be looking at using trigonometry to solve unknown side lengths and angles of right-angled triangles from written information. So from written information you're going to need to be able to draw your own diagram. So in this problem we're going to do 4 examples, just a heads up. So in this first example we have a rectangular gate, has a diagonal piece of metal joining the opposite corners. So let's just draw it. Apparently doesn't want to draw. So we have a rectangular gate. It has a diagonal piece of metal joining the opposite corners, so there's some sort of cross beam. The vertical height, so vertical is up and down, remember? So the vertical height of the gate is 2.1 meters. Obviously it's a rectangle, so it's got right angles everywhere. The diagonal piece makes an angle, so the diagonal piece makes an angle of 50 degrees with the horizontal. So remember the horizontal is, think about the horizon, so this piece here is the horizontal. So the diagonal piece, this diagonal piece makes an angle of 50 degrees with the horizontal. How long is the diagonal piece of metal? So what we're trying to find out is this diagonal length. So that's our x. That's what we're trying to find. So we simply just have a right angle triangle. You don't have to redraw it out, but I will just quickly. 2.1 meters high, 50 degrees between the horizontal and the diagonal piece, and then our x. So then first thing we do is label our sides. So 50 degrees, so this is opposite, and this is the hypotenuse. We then use our trig ratios. Opposite and hypotenuse is sine, so we'll write out sine theta equals opposite over hypotenuse. And then we'll substitute in what we've got. We've got sine 50 equals our opposite side, which is 2.1, divided by our hypotenuse side, which is x. Then we'll rearrange the equation. So it'll be x equals 2.1 divided by sine 50. And if we type that into our calculator, we'll get a number. 2.1 divided by the sine 50 gives us 2.74, which seems reasonable. And that is in meters. So trigonometry, like you've been doing, except this time we've got to draw our own diagrams. Now, you also need to be able to solve problems involving angles of elevation and depression. So an angle of elevation is when you, the observer, are looking up towards an object, and the angle of elevation is in between the horizontal. So imagine this is your eyeball. So the horizontal looking up to the object. That's the angle of elevation. Now an angle of depression is slightly different. An angle of depression is in between the horizontal and looking down to an object. So this angle of depression is used when we're up high. So if we're up high on a balcony or a lighthouse, and we're looking down towards an object, the angle of depression is between the horizontal and the object, looking down to the object. We'll do an example of an angle of elevation and an angle of depression. So our next example is from a point 235 meters from the base of a cliff. So we've got a cliff from 235 meters from the base. So the word base is the bottom. So from the bottom of the cliff, so 235 meters from the base of a cliff. So this is our cliff. And 235 meters from the base of the cliff, the angle of elevation to the cliff top is 25 degrees. So if we're here and we're looking up to the cliff top, the angle of elevation is between the horizontal and looking up towards the object, which is the cliff top. So the angle of elevation is in here. 25 degrees is in here. Now obviously the cliff is at a right angle, so we have a right angle triangle. And now what we're trying to find is the height of the cliff. So the height of the cliff is x. So the first thing we want to do is label our sides. We have our opposite side, we have our adjacent side, and the one linking opposite and adjacent is tan. So we're going to have tan theta equals opposite side over the adjacent side. So tan, substituting in our values, tan 25 is equal to our opposite side, which is x, divided by our adjacent side, which is 235. And then to rearrange this one, we need to times both sides by 235. And we'll be left with x is equal to 235 times by tan 25. And if we type that into our calculator, 235 multiplied by tan 25, we get 109.58. At some stage, I will get us to do an activity outside where we measure the angle. So we look up at an object and we measure this angle using an inclinometer and how far away horizontally we are. And then we can work out its height just by measuring this angle and this distance. Now, third example. So, from a vertical cliff 80 meters above sea level. So, we have the sea, we have a cliff, and the cliff is 80 meters above sea level. So, we have a height of 80 meters. Vertical cliff, a whale is observed at an angle of depression of 6 degrees. So, if we look at our diagram again, the angle of depression, so we're at the top of the cliff. This is a cliff. We're up here. Now, angle of depression of 6 degrees. So the angle of depression is in between this horizontal line and looking down towards the whale. So let's just say the whale's here. So the 6 degrees is between, if you look here, the horizontal and looking down to the whale. So that's 6 degrees. However, where's our right angle triangle? Right angle triangle's here. So we've got our 80 meters high vertical cliff, we've got our right angle, we've got 6 degrees. So usually what I do is we can use something called alternate angles. I'm not going to prove this to you, but if you have two parallel lines, then, and if you cut these two parallel lines with a diagonal line, this angle in here is going to be equal to this angle in here. So this angle in here, we have parallel line, so sea level is parallel with the horizontal. This diagonal line through here, this angle here is going to be equal to this angle here. So this little angle down here is also 6 degrees. So now we have our right angle triangle. We have a side, we have an angle. So find the distance between the observer at the top of the cliff and the whale. So find the distance between the observer at the top of the cliff and the whale. So we're trying to find this hypotenuse distance, this direct distance between the observer and the whale. So this is our angle here, so we need to label our sides. This is our opposite side, this is our hypotenuse side. So sine links opposite and hypotenuse. So we'll have sine theta equals the opposite side divided by the hypotenuse side. So substituting in our known values, it would be sine of 6 degrees equals our opposite side, which is 80, divided by our hypotenuse, which is x. Rearranging this, we'll get x equals 80 divided by sine 6. And therefore, typing into our calculator, 80 divided by sine 6 is 765.34 meters. So there's a large distance between us and the whale directly from here to here. Our last example, a bit more complicated. A television antenna is mounted on top of a nearby hill. So we have a hill. we have a antenna. That's the antenna. So a television antenna is mounted on the top of a nearby hill from a position of 4,500 meters away. The angle of elevation to the bottom of the antenna is 17.5 degrees. So remember, angle of elevation is between the horizontal and looking up at the object. So the bottom of the antenna is here. So the angle of elevation here is 17.5 degrees. So that's 17.5 degrees. Whereas the angle of elevation to the top of the antenna is 17.9. So that angle there is only slightly bigger, 17.9 degrees. Find the height of the antenna in meters. So we don't have any information about this side here. All we've got is how far away from the base of the hill we are. We're at 4,500 meters or 4.5 k's. And we've got two angles of elevation. We've got the big triangle and the small triangle. Well, let me just draw this up into two smaller triangles quickly. So we've got the big triangle, which is 17.9 degrees, 4,500 meters. And we have the smaller triangle, which is 17.5 degrees, still 4,500 meters. And we want the height. So what we could do is we could find this side here for the big triangle and this side here for the small triangle and do the big triangle, take away the little triangle, and we'll have what's left over, which is the antenna. So we need to find we need to find the big triangle side. So this is our opposite side. Let's just call this side X. So we need to find this opposite side, X, and this opposite side here. And let's just give that a different letter. Let's call that Y. So Y is our small triangle side, and X is our large triangle opposite side. And again, this is adjacent, and this is adjacent. So we're actually going to need to do two calculations. We're going to have to find X, and we're going to have to find Y. And then this antenna is going to be the large one, which we called X, take away the small one, which we called Y. So I don't have a lot of room because I drew my triangles way too big. Let's solve for Y up here. So we've labelled our sides. We've got opposite and adjacent. So what one links opposite and adjacent? We've got tan. So it'll be tan theta equals the opposite side over the adjacent side. So we're going to have tan of theta, which is 17.5, equals the opposite side, which is Y, divided by the adjacent side, which is 4,500. And if we times both sides by 4,500, we'll get Y equals 4,500 multiplied by tan 17.5. And if we type that into our calculators, 4,500 times by tan 17.5, we will get a distance of 1,418.84, and that's in meters. So that's for our small triangle. So the hill is quite high. So for this larger triangle, we'll do the working down here. We'll have, again, it's opposite and adjacent, so it's tan. So tan theta equals opposite over adjacent. So tan of 17.9 equals the opposite side, which is X, over the adjacent side, which is 4,500. Rearranging, we need to times both sides by 4,500, so we'll get X equals 4,500 multiplied by tan 17.9. And if we type that into our calculator, we will get 4500 multiplied by 10, 17.9. So that'll give us 1453.46 meters. So obviously the bigger triangle was slightly higher, 1450 versus 1418. So now to find the height of the antenna, we're going to do the large number, which is the 1453.46, subtract the small one, which is 1418.84. And if we type that in, 1453.46 subtract 1418.84, we'll get 34.62 meters. So we actually could work out the height of something up on a hill by measuring the angle to its bottom and then the angle to its top, and then using tan theta to work out the sides, and then we worked out the difference between them to get the height of the antenna. That's about as tricky as a question will get for you. Hopefully it made sense. I'll definitely be back on Thursday to help us, but otherwise you guys just need to keep working through problems, be as productive as you can. I'll see you Thursday. Cheers.